We have two excellent presenters. We have a solution architect, Don, who is a storage expert, and we have a product manager for our storage and networking, Mark, who are going to be here to present on the use cases, practical use cases around storage. There's also another storage track or storage session that they'll tell you about as well. So there's two storage sessions today. So welcome, Don and Mark. You ready? Take it away.
Thank you, Jim. So yes, welcome. Use cases and practical solutions for Docker container storage on Swarm and Kubernetes. Doesn't really roll off the tongue, but does describe what we're going to talk about. So, quick introduction. One of the important things I think with storage is it's important to everybody in an enterprise deployment scenario. And we understand from all you folks, both this week and prior to this week, that storage is a concept on many, many people's minds. And so in this talk, we want to address some of the specific areas that people have asked us, both here and prior to this, and come back with some answers. So the agenda is we're going to look at some what we call storage fake news, some application workload evolution, so applications and the types of applications we're in on container platforms are changing. Container persistent state, some use cases, some storage solutions, and then we're going to move into two demonstrations. I'll be doing one on Microsoft Windows and Azure storage, and my colleague Mark will be looking at Kubernetes. So, storage fake news, myths in container persistence. Storage has been a topic people have talked about quite often, and being one of the things people frequently mention as, an opportunity, shall we say, with containers. Statements such as persistent applications should not be running containers. Containers are for stateless microservices. No, that's fake news. It's true that we need to externalize storage outside of the container. We don't want to keep storage in the container because the container is ephemeral. But we can run persistent applications in containers. The second myth, following on from that, a little bit more specific, some persistent applications are okay, but never run structured databases, SQL, NoSQL databases on container platforms. Many articles on the internet for that. No, fake news. If you actually look, nearly all the major database vendors already have container images that they support and provide to everybody on their different hubs and repos. And in this case, Oracle and MySQL are Docker certified for Docker EE. Mark will cover the certification a little bit later in this talk. Myth number 3, there are no storage options for Windows containers. So if people think storage is difficult on Linux, or that's at least the perception of what's available on Windows is even worse. No, more fake news. There are Windows solutions that we can use in enterprise scale deployments. And those consist of a number of Microsoft technologies: storage spaces direct, cluster shared volumes, scale out file server. And I'll be doing the demonstration using those technologies later on in the talk. So storage, why do we need a new approach to storage anyway when using containers? We've had storage a long time, storage concepts, storage hardware. What's new? Historically, storage provisioning may have had separate teams to do that. You would put a request in, you'd get storage allocated, and then you, as an application team, you could leverage the storage. But the storage really was bound to hosts or environments. It wasn't per application storage necessarily. So one of the changes with containers is it needs to evolve and be more application-centric. And today they need to be API-driven and instantaneous. If we can horizontally scale containers out in milliseconds, and we cannot scale the storage to go with that application out in milliseconds, no good. So we have to have storage solutions that help and support us in that provisioning. Also, applications are changing. Application workload evolution, the data explosion. What are the use cases we need to consider when designing and implementing these containers and solutions for storage? Let's take an example of a customer of ours, GSK or GlaxoSmithKline. They're introducing new and innovative applications in containers, much higher scale, performance and availability requirements than the traditional applications. Containerized apps that have more churn. I mean, these are supposed to be ephemeral. They're supposed to come and go on an as-needed basis. And apps that are more distributed and have more distributed area. GSK came to us and selected Docker Enterprise because we supply a multitude of tools and technologies and interfaces so that their scientists can run data analysis at scale. So what do we keep talking about this scale and data for? If we take a look at the autonomous car from Google, just as an example of how data rates are changing. It generates 1 gigabyte of data per second from all its sensors. In the US, the average person drives their car for 600 hours a year. That's 2 petabytes of data per vehicle per annum. Now, it's true, all that may not come off the car, it might not be externalized, but even if a percentage of that does, the volumes are huge. Especially when there's 264 million cars in the US alone. I'll leave you to do the mathematics of those numbers, but they're very big. So, we're not storing that quantity of data directly in our application containers, no matter what we try to do. We have to have better storage solutions. And even when we look at the application data, that's not the end of it. We have auditing data, logging data, monitoring data. All that goes on top of it from our infrastructure. So we've created this layer cake of layers of data that we need to store and persist. And not all storage solutions meet every one of those. There's different variations that are better in the storage space for different aspects of data. So, contagious storage requirement. What we're going to look at in this talk is very specific. Regardless of the lifespan of the container, any necessary long-term storage should always persist. The life cycle of the container and the storage is not necessarily the same. The container could and should be able to be scheduled to run on any node in the cluster or zone. So in zones, that could be different data, physical data centers in on-prem, or something like an availability zone in AWS. So the use cases. I talked about GSK and the innovative application, but our other legacy applications there as well, things like CRM, CMS, data warehousing, big data. We still need to support those on our platforms. And we also need to look at the new modern applications, so AI or machine learning, IoT, genomics, and media processing. Each of these applications has a number of properties that it needs to do with its data. Things like, what latency do I need to access it? IOPS for read-write. Availability, volume size, transactional and non-transactional access to that data. Durability, scalability, and accessibility. We'll cover these in a few seconds. And then there's different types of storage available. Whether it's on-prem or in the cloud, there's not just one storage option. There's file storage, block storage, and object storage. So if we dig in and have a look at kind of each of these and how they hang together, file storage usually used by applications. The workloads are usually low IOPS, medium latency, high availability, and low data volumes. They're transactional, medium-term storage, access counts and speed. And they're medium cost. So what technologies? NFS, SMB are the traditional ones. If you take those concepts up into the cloud, things like AFS or EFS, you would use for file storage. For block storage, that's traditionally what we would store databases on. High IOPS, low latency, high availability, high data volumes, and a mistake there because it says non-transactional, it should say transactional. Storage-wise, iSCSI and Fibre Channel are on-prem historical solutions, and things like Amazon EBS, Google Persistent Disk, or Azure Disk Premium Storage. And the reason we say things like premium storage is these are the sort of applications that need to be on the fastest SSDs. Really slow latency. Hard drives, no. Object storage, that's more, today it can be application storage, key value pair type storage, used by monitoring and logging, and that's used by big data warehouses, log processing and monitoring. So all that over-the-top data that we were talking about, things you would push to your Elk stack for your logging, etc. This is the sort of storage you would use. Maybe different to the application storage itself. And just to reiterate, how should the life cycle of storage match the life cycle of your application? The two are not inherently bound together with containers. I stack containers up, I close them down. I don't necessarily want my data to go away. So we're not going to look in this talk at any forms of pure host-based storage, all the things we learn first when we're using Kubernetes or Docker Swarm. What we need to do, again, to reiterate, is storage that allows us to run our application workloads anywhere in our cluster, and the storage to be available exactly when the containers need it. There's multiple access methods as well. So we have storage where we only want a single container to access it. And in that case, it's things like we may be able to relocate that volume in the case of a storage failure across, in AWS, for example, across an availability zone. We have multi-container or pod access. So we have many different containers or pods accessing the same data. And then we need to enable either read or write access based on that. So now let's take a look at the container storage landscape. And for that, I'm going to hand over to my colleague, Matt. Thanks, Matt.
Thank you, Don. Let's make sure I'm pressing the right buttons here. Perfect. So it's understandable that the storage landscape is hard to understand because it is highly fragmented and it is vast. There are a lot of storage drivers that exist out there, almost as many as Kubernetes distributions. And they all have different feature sets in different areas that they support. There's a couple good ways to kind of to look at this. Well, let's look at it by orchestrator and try and segment all the components out, right? Because within a container orchestration stack, there are the storage driver plugins that are specific to different kinds of environments, have their own feature sets. There is the container orchestrator itself that has interfaces for these plugins to plug into. And then there are methods that these plugins use to then connect the storage directly to the pod or container so that the application can access the storage. And this is all wrapped up by Docker Enterprise that has opinionated workflows to help you manage the storage and help you through this process. And let's look at a way of kind of slicing and dicing storage and evaluating the different kinds of storage drivers that exist out there. One helpful way to look at it is who created this storage driver. And this is definitely not an exhaustive list, but I think it's helpful to look at it this way. Say, we have drivers that are cloud native. And so these are provided by the cloud providers themselves, and they are utilizing the native capabilities, the native storage primitives of the cloud platform. And so these drivers connect your events from your orchestrator to the native primitives of that cloud. And then we have software-defined storage vendors. So these are storage drivers that are purely software-defined, very, very flexible in the number of environments they can be deployed into. They accept block storage, and then they represent a storage layer to your application, providing all kinds of extra features on top of it. So very flexible, except you're going to pay extra because you have to pay that software-defined storage independently of the storage that it's consuming underneath it. And then lastly, you have your physical storage drivers, right? So this is your NetApps, your EMCs, vendors that provide storage plugins that give you special integration into the storage backend that they use. Now, in most cases, you've already paid for this, right? Because you have the storage array, you're not paying extra for the driver. It comes implicit with the hardware that you purchased. And so with all these different ways of connecting our containers to storage subsystems, we can see there's kind of a spectrum, right? Software-defined storage, very flexible, works in a lot of different environments. Then we have cloud storage drivers and physical storage drivers that are specific to the storage subsystem or to the cloud that you're in. And then, of course, there's also the manual way that we've done it for a long time before these drivers started to appear, right? So this is connecting iSCSI or NFS or Fiber Channel directly to the host and then presenting that manually to the container, or using the APIs on the cloud side directly to do the same thing to basically configure host-level storage and present that to containers. Not an ideal scenario, we're moving away from that, but that is an option if a specific driver is not available. So let's look at Swarm, and I just want to talk about a few options for Swarm that we have. So we have a certified storage driver program in which we certify drivers to make sure that they work with Docker Enterprise. And so for Docker Swarm, there are certified storage drivers available, but there's also a driver that I want to mention called Docker Cloud Store. This is a driver that was built and supported by Docker Inc. That provides integration with AWS and Azure. And so you can orchestrate storage through that so that the storage is provisioned, deprovisioned, moved around depending on where volumes are scheduled within your Swarm cluster. And so that's a really neat option for Swarm. On the Kubernetes side, Kubernetes, like a lot of things Kubernetes does, things are a lot more complicated, but we also get a lot more power in some ways with that. And so a couple storage concepts that I'll mention very briefly. I will say, please go to a talk there's a talk around 3 o'clock on storage that dives very deep into this and also talks about CSI. So if you're interested in learning more, attend that talk. But in general, there are some concepts in Kubernetes that make storage very nice because it modularizes it, and it also gives us an ability to kind of push policy into how we interact with storage. There's a couple concepts. Persistent volume claim, and a storage class. And one analogy I use to kind of explain this in a really nice way is it's kind of like renting a car. Because when you're looking for a car, you're looking for kind of a generic type of car. You don't want like an individual model like that's red or something like that. You were just thinking you want to rent a car. Same with storage. You don't want the developer to be really aware of the type of storage that's underneath or how it's configured or connected to the host. And so when you go to Enterprise Rent-A-Car or whatever, you go in, you look at, you ask for a compact car, so that's your storage class. And then you make the reservation, that's your persistent volume claim, right? It's your ask for the storage. And when you get into the Enterprise Rent-A-Car, they give you the car, that's a specific car, and that's your actual volume that is then bound to your claim. And so that's kind of a nice way of kind of understanding how we're abstracting the specifics of storage and the provisioning of storage away from the developers, because we really don't want them to be aware. This is nice because then when you're deploying on any type of cloud or on-prem environment, the specific type of storage does not have to be presented in any way to the people who are actually deploying applications. And again, I'll just mention, we're going to do some demos to show you some aspects of this, but that one part of Docker Enterprise is the certification of these drivers. Now, in the early days of Kubernetes, there was storage drivers that were built directly into the code base of Kube. And this is nice because the community contributed on it, but now, especially with CSI, the driver code is being taken out of the Kube project and maintained directly by developers and the storage vendors. This makes storage certification a little more important because it's a little bit more far away from the project. And so certification is essentially means tests and validated. There's a customer support relationship so that a support case that comes in through Docker or the storage vendor can be collaborated on. There's a legal agreement that can happen. I mean, these are your bits after all. You want them to be safe. And then, of course, it's kept up and reevaluated on an ongoing basis. So that's what certified driver means. And next, I think we have time for demos. So I'll invite Don back up to the stage, who is going to do a Swarm on Windows storage demo for us. I know it's been highly requested. And then I'll come back up and do a Kube storage demo for you. Thank you.
Okay. Thank you, Mark. So actually, there's a little bit around Cloud Store as well at this point, just before we dive into some of the demos. The Cloud Store integrates with the persistent data volumes of their cloud environment, which Mark already had on the slide. But one of the reasons that we put Cloud Store together was to make it easy to use and also to be able to share data across the tasks and node in order to give us our enterprise storage. The thing is, you can put it in your YAML, in your compose files, and you can define everything in there. So it's still declarative, not an easy word to say when you're on a stage. But it fits in with your normal configuration for your platform as well. So it's not something else that you need to worry about. Cloud Store for AWS. So Cloud Store comes in two different flavors, AWS and Azure, again, as Mark mentioned. And we covered off quickly earlier different aspects, the single or multi-volume, multi-container access, and about replication and failover of the storage and relocation. So on the slide here, we've got single access and multi-access, and we've got the Cloud Store AWS plugin. So it's a plugin to the engine that we can install using the Docker command line. And that plugs into Swarm and allows us to access, in this case, EBS on Amazon, the block storage, or EFS, the file storage. The single access is onto the block storage. Now, normally there's only one container that would access that, except maybe it's a HA application, you've got a master and slave, and actually the slave's listening to it as well in order that it can take over from the master in the case of a failure. We don't usually have many containers reading and writing to this. This is the one that in the case of a storage failure will get relocated and the container will still be able to access it. In the case of multi-access, this is where you've got multiple access. That doesn't mean everybody's got read-write. You can control that as well and say whether it's read-only or read-write access. But that uses the file system. In the case of things failing, then it's in the zone where it is. But obviously, Amazon EFS, they handle a lot of the storage concepts and failures as well for you. How do we do that? So in order to use Cloud Store, it simply requires you to install a plugin. Docker plugin install, specify an alias, in this case Cloud Store AWS, set your permissions, and then set up the AWS region, your stack, and whether EFS is supported. It also has regular and max I/O. So where we're talking about fast access and slow access, that's where max I/O comes in for the fast IOPS, and the regular storage doesn't. When you start your container, much like the persistent volume claims, you can actually start your container and say what type of storage you want, and it will get handled by Cloud Store. For Azure, not quite as rounded out. There's the single backing option, which is the multi-access. So we can have multiple containers accessing that storage, and that's backed by the Azure file system. And unsurprisingly, the command looks very similar. You just tell it Cloud Store Azure, and the fact you want to change some of the variables which are Azure specific for the storage account. So, finally, just to that click point on the storage for Windows. I'm going to give you a quick overview of what the application is. I'm not sure everybody in here knows wants to know about Windows storage, but at least this gives you the 10,000-foot view of what we're going to go through. So anybody that saw the keynote speech on Tuesday will have seen the famous pet shop application, .NET 3.5 application, which is basically just a web application where we can browse pets, put them in a shopping cart, and buy them. It's a traditional 3-tier application. So it's a web application with a web service and a database. So things, we've been developing for years. It was last updated in 2008. I don't think you call it bleeding edge. But it is a Windows MTA application, which is a modernization. We can move this forwards in time from 2008. We can deploy it on Windows Server 2016 or newer, and we can hook it into the whole on-prem Windows or Azure storage stacks and make it highly available and resilient. This diagram is quickly showing what's set up on Azure, because today's demo will be running on Azure. There's an Azure resource group, and in that group we have our container host, which is running our .NET application, and Microsoft SQL Server to access the database where the pets and the shopping cart information is stored. There's an Active Directory server down there because the two green boxes, S2D1 and S2D2, are the storage spaces direct servers. They're bound together in a highly available cluster, and that cluster requires Active Directory. So we've just got a primary domain controller. In the real world, there will be secondaries and resilience. But the important point here is that line of text between the container host and the green boxes at the bottom. That's where we define our storage that sits on our cluster, and we can map that into the containers. That's the high-level view. I'm quickly going to show the non-high-level view, which anybody that's interested in Windows will probably be interested in seeing. We start at the bottom. We've got a storage pool we create across multiple Windows servers running on Windows Server 2016 or newer. Storage Spaces Direct basically allows us to pool and collect that storage from the individual hosts. In this case, they're VMs with disks attached in Azure. Cluster shared volumes then allow us to present virtual block device volumes on top of that. And then the SMB3 file share is the Windows scale-out file server that then allows us to expose mounts as directories, much like NetUse and other type things that have been used historically. But it allows us to use those in containers and bind it in. For anybody that wants to see what we're about to do, there is a GitHub directory there, and within that GitHub directory there's an application folder, and you will see the Docker Compose file that we're going to run for Swarm. I'll give everybody like a frantic few seconds, but not too much for those that want to follow. Okay. So that was my point to do my demonstration. So I'll quickly jump out of here and go over to my Microsoft Windows Remote Desktop. But first, I'll quickly show you. This is Azure. This is my resource group. There's lots of things in there. But if we quickly just take a look and go down to the VMs, virtual machines, and filter on that, you can see S2D1, S2D2 storage server, and the SQL Server node, which is actually where I'm going to be deploying the application, and MS SQL on there as well. So going over to the remote desktop here, this is now the SQL Server VM host on which we're going to be running this. And you can see I'm on something called G Drive SQL data. If I quickly grab, this is the compose file we'll be using. So this defines the services. We've got the Pet Shop DB at the top, where we map in this G drive SQL data into the C drive SQL data of the container. The container is a Microsoft SQL Server Express 1709 image. And we expose a port 11433, which is the MS SQL Server, but on the host, but with a different address. The important section here, though, is underneath in the environment. The attach underscore DBS. When we start the SQL Server container up, we're going to bind the databases from the shared storage. Every container we start up, we can point to the files on the shared storage. When the container goes away, the shared storage does not. Below that, then we've got the web application itself. The HTML pages are there, and then there's a web service as well. We're not really looking at the web service in this demonstration, but it's deployed as part of the stack in our compose file. Now, we've already created the storage, but this line here that's highlighted is the command you run on the nodes normally. And I apologize for the glasser thing, but I can't see both at once. And you create a new SMB global mapping. We set the remote path to be on our storage server, and we map it into the local path of G. So the G drive in our command shell is our mounted volume. And we can see that on the host by running this PowerShell command, get SMB global mapping, which if I just run in there, just reinforces that our shared storage is mapped as the G drive. On the G drive, we've created an SQL data directory into which I put some of the contents of the GitHub repository, which is a script to generate all the databases that we need for our pet store application. I haven't come here with the database already pre-set up, so I wish somebody had given me some grapes. I'm now going to start up a Windows. He says, hoping he's got this open in his tab, which he hasn't. So we'll have to rely on the good old backspace. What I'm going to do here is actually create my database. How am I going to create my database? I'm actually going to start an MS SQL Server up, and then I'm going to run some scripts to create and provision the database. And then I'm going to start my compose stack up and map that database that pre-exists into my running application. Actually, before I'll do that, I did it already actually. If I do a dir, you'll see that the only things that are in there are the install databases script, which is the one we'll be using. So I'll quickly start this container up. This is where I found I ran it this morning to test it, and I didn't delete the image. That's what happens when you use the back prompts rather than using what you'd set up. And so I've started that up. And if you notice on the start, I've got the -G, the -V, and then mounting this partition, the shared one, to the C SQL data. So I can now go in and do a docker exec -IT to SQL enterprise and just run a command shell to get inside that Microsoft SQL Server container. Thank you. If I do a quick dir in here, you can see the SQL data directories there, and you can see it's got a load of hieroglyphics in there that shows that this is actually a mapped container path rather than being on the local node. And so with that, I'll change into the SQL data and look what's there. And obviously, that's the directory I was in on the G drive before I started the container, so I can now see my install script. So I'm going to go ahead and run that. And what this does is it creates a database tables, it installs data in there, it says permissions up, and because it's an ASP.NET ASP.NET application, it also needs to do some things to make those pages cacheable from the web browser as well. So this is a login, then we'll put the data in that we need, all the pets going into the pet store, and then from that point we can close this container down. Because this is not the application we're running, I'm merely just creating the actual databases physically on the share. And all this activity, this build activity, is the same build activity from 2008 on the .NET application. We've not changed anything here on the MTA to move it into the container. So there we are. If I do a dir, you can now see on the screen the MS Pet, Shop 4, MDF, the Pet Shop for orders, database, and a profile database. So they're now running logically within our container. If I exit from my container and do a Docker RM on SQL, enterprise, just to make sure my container's gone, which I think it should have because I started it with the RM option. Yep, no, it's running. I didn't start with that. Okay, so now I'm back on the G drive, the shared partition mounted on the file server. Here's all my databases that I've got. Quickly recap, if I go back over to my compose file, this is the attached DBS line here, and in there you can see those same names of files that we just saw on the file system. We're telling Microsoft SQL Server to bind these pre-existing databases into the container when it starts. So to do that, I'll just jump across to the F drive, which is where my GitHub repository is cloned, and I'm just going to do docker compose -f. Oops, I'm not in the right directory. And we're going to start bringing our containers up. In the compose file, the web application and the web service, I've got dependency on the database. So they're not all going to start in parallel. It's going to have to wait for the DB to come up. And in a second, you should see the SQL Server output, and you should see the fact that it's saying it's attaching three databases, sorry, which has just gone past. And it's now bound those databases into my container. Which means, if I now go across to what is hopefully my pet store application in a second, and press enter, we should get the application that represented the screenshot. And of course, I didn't have a grape. Okay, I would have to delete it and take a quick look at that. But fundamentally, at that point, we should have the pet store application up that you saw. And we can take it from there. So, thank you very much.
I'm beginning to think it's not the grapes. All right, we'll do a very quick lightning round kube storage demo. And what I'm going to be showing you is a I'll be showing you the demo. We've run it on AWS. We're using the AWS Cloud Provider flag, and so we're going to be using Elastic Block Storage to do this demo. And what I have right here is I have, let's see, bring it up. I have 4 nodes running, 3 workers, 1 master, very production-worthy scenario. And I'm just going to deploy a very simple app. And what I have here is I have an Nginx web server that is exposed by a service. And it has a persistent volume claim to a specific storage class named standard. Well, in Docker Enterprise, I can see here that I have a couple storage classes that exist. So if I go over to storage, I have one called backup and I have one called standard. Backup is for slow storage in AWS. Standard is for the standard storage. This is nice because then I can have the same terminology no matter where the application is deployed. It could be in a different environment, and you could reference the storage provisioner just by using the storage class. And so let's take this and deploy it, and then see that it works. Okay, the app is going to take a couple seconds to come up. Let's see. What I'm going to do is I'm actually going to shell into it, and I don't think it's up yet. I'm going to write a file into the app so that we can see that there is persistent state running in the container that's mapped to the volume. Okay, so here we'll just write a quick message. Welcome to DockerCon. Just so you know, I'm not cheating. What's your name, sir? Lars. Lars. Welcome to DockerCon, Lars. Okay. And we'll put that into index.html. And now we go to our app. It should say, welcome to DockerCon. Lars, there we go. Okay, so we've got our app up. Cool. Yeah, that wasn't anything. We just deployed an Nginx container. Come on, guys. You're easily impressed. I like it. So one thing that I just want to show, though, is if we go to storage, we have our persistent volume here. It's PVC A6. Over in EC2, we can see that we should have a volume that maps to this. Let me just make sure I'm selecting the right one. Oh, that's actually, let's see. If we click on it, there is a label here somewhere that corresponds to the actual volume, A6. Well, I think this is it right here because it's attached. So then let's go ahead and kill the pod, see what happens. Just make sure things are actually working as intended. So we'll just remove that pod right there. And if we go over to our console here, we should see things getting rescheduled. Let's see, it looks like it's not attached right now, so it might be reattaching. So the pod should be coming up right now. It's on a different host. And once it comes up, this is super exciting. And there we go. We can see that the pod has been rescheduled. The volume has been detached from the host and reattached to another EC2 instance where that pod is, which is actually another example of how using cloud native storage is somewhat different than using a software-defined storage, right? Because here we are actually detaching a volume between different EC2 hosts as opposed to using some sort of replicated storage layer for us, right? So just gives you an example of the differences between using cloud native and software defined. So that is the demo. Thank you for attending, Lars, and thank you everybody else. Now we'll bring Don back up on stage and ask for questions. There isn't a mic, so you're just gonna have to come up or yell it, and then we'll repeat your question.
Any questions?
I think Jim's got one.
Oh, great.
Hi. Question regarding Cloud Store and Azure. Do you have a ATA roadmap for block storage availability?
Great question. Yeah, it's been a request. It hasn't been officially committed to a roadmap yet, but how about you find me after this and we'll chat about it.
Okay. Any other questions?
A lot of people sit in their seats. They want to wait for other questions to come. Someone has to be brave.
There's one there.
This is like when the credits for others one.
Oh, yeah.
Could you show us how do you set up the storage class?
Yes. It was quite simple. So I'll go back to my GitHub page. So by the way, this is just Mark-Church storage demo, if you want to check it out. I have the storage classes here, and we can see I've got two storage classes, and they are both using Kubernetes IO AWS EBS provisioner. Now, one big note is this is the in-tree driver for AWS. So the code for this driver actually resides within Kubernetes itself. In Kubernetes 1.13, which we are going to be supporting in the next release of Docker Enterprise, we're also going to be supporting CSI. So the interface for the storage provisioner is actually going to be different. It'll be externalized from kube. But in this case, because it's today and not in our next release, this is the in-tree provisioner for AWS. And the parameters that we chose is GP2 for the standard storage and the cold storage SC1 for the backup storage. Actually, I think this guy had a question over here.
Okay, thank you for your session and for sharing all the knowledge. My question is regarding the relational databases that are always big topic regarding storage persistence. How well the big and well-known relational databases like SQL Server or Oracle cope when you are changing to a new node? The container has to be reinitialized even if you are persisting the database information in the volume. Do they behave well? I am asking regarding real-life experience with that. So if the database behaves well, is able to initialize in the right way, what is the behavior when you have this kind of nodes go down, databases go to another node, and then we have the persistent storage, but the database has been reinitialized?
That's, again, a fantastic question, real world versus talk time. I actually have a longer video when it worked last week. And I deliberately actually go into the cluster and I fail one storage server down. I fail the second storage server down. At that point, the application's got nowhere to go. It's still got its mount. It's still got it thinks it's still got shared storage. It has nothing. You get a failure in the application, and then I bring one node back, which suddenly comes back. The application continues working as if there was nothing there at all. So I'll see about, I don't know, maybe we could do something about getting that video up. I might reshoot it because it was just for the purposes if it failed and I had more time. But we'll get that back up there. And that shows you a real world example of yanking the whole storage cluster out from underneath running containers and it coming back as soon as that highly available cluster comes back.
Okay, thank you.
Thank you, gents. Is there a way, from an operations perspective, in the enterprise or in the UCP UI, when you looked at the different classes, to be able to see what that maps back to on the back end, without having to go and look at your YAML files?
Yes. So you want to see which provisioner is mapped to the storage class, or you want to see which volumes map?
So like if you were to give it a friendly name within the UCP UI, if you can even do that, can you then map that back to what it is on the actual back end, just looking at the UI?
Yeah, you can. So if I go over storage, and we're actually revamping the UI right now because this isn't so great. One thing we want to do is we want to be able to connect this to all the volumes that exists. So a storage administrator can look and see, okay, what are all the apps that have provisioned storage from this class, and let's map that back to the storage. This is more of like an application deployer's view. So we can see here, here's the original YAML for the storage class. But yeah, we're working on making it a little bit better for a storage administrator to view so they can see kind of from a storage to app perspective rather than an app to storage perspective.
Any more questions? Nope.
Cool. So we have one more talk at around 3 o'clock if you want to dive deeper on this. Thank you for attending.
Yeah, thank you very much. Have a great DockerCon.